The derivation of the derivative of arc cosine is very similar to the derivation of the derivative of arc sine. And in a moment, I'm going to have you pause the video and work that out. I just want to remind you, though, of the definition of arc cosine. So I've started here with the graph of cosine, and we know that what we need to do is restrict the domain, and then we'll take the inverse of this function. This won't be the inverse. This will just be the invertible function whose inverse becomes arc cosine. So the rule is we need to choose an interval that corresponds to 2 quadrants worth of angles. One quadrant where cosine is positive and one where it's negative. And one rule is that we always choose the standard copy of quadrant 1. So that would be the interval from 0 to pi over 2. That gives me that piece of graph. Now I can see here I can't make the same choice that we made for arc sine. There we chose quadrant 4, going from negative pi over 2 to 0. But if I chose that, we'd repeat our positive values instead of getting our negative values. So if I want the connected piece of graph where I get the negative values, I'm going to want to come here. So I'm going to want to go from pi over 2 to pi. That corresponds to quadrant 2. I wouldn't want quadrant 3 because I want to get a connected piece of graph. If I just look at quadrants 2 and 4, 2 is the only one where cosine is negative. So if I were just looking at this picture, I could still sort of see that it's got to be 1 and 2, but I like to go back and forth between the two different depictions. Here the angle is moving to the right, here the angle is represented rotationally. So we restrict the domain so that we get that x is in the interval from 0 to pi this time. And then we can take the inverse of that, and that will give us y equals arc cosine of x. The graph isn't super important, but I'll go ahead and draw it for you. Looks something like so. Here, this was the point 0, 1. When I graph the inverse, it becomes 1, 0. This was the point pi, negative 1. When I graph the inverse, it becomes the point negative 1 pi. I will just mention that the graph of cosine with restricted domain has horizontal tangents at the endpoints. So just like with arc sine, this graph here has vertical tangents at the endpoints, so that we can expect that the derivative will not be defined at 0 and pi, although arc cosine is defined at 0 and pi. So y equals arc cosine of x I get by simply switching the roles of x and y in the formula for this function. So I'm going to write that down on the board. That's going to mean that that x equals cosine of y, and y is in the interval from 0 to pi. So I want you to pause the video, use this description of arc cosine together with implicit differentiation to find a formula for the derivative of arc cosine. And you should be able to simplify it to the point that you're describing it just in terms of x. And just like with the derivative of arc sine, you should be able to describe it without any trig or inverse trig function showing up in your formula. Okay, pause the video and do that. This is kind of interesting. You should have gotten exactly the opposite of what you got when you took the derivative of arc sine. We get negative 1 over root 1 minus x squared. Now, if you got that and you remembered to justify choosing the positive square root when you solved for sine y, you can go ahead and skip the rest of this video. If you want to talk through this derivation together, stay tuned. Okay. So what I did is I started with this equation that gives me the relationship between x and y, and just took the derivative of both sides. Derivative of x is 1. Implicit differentiation tells me that the derivative of cosine y is negative sine y times y prime. We solve for y prime, dividing through by sine y. Okay. Now, sine y will be 0 at these endpoints, at 0 and pi. We saw that's where the graph has a vertical tangent, so we don't expect the derivative to be defined there anyway. Then I come over here, and I use my Pythagorean identity. sine squared plus cosine squared of anything, in this case of y, is equal to 1. So sine squared y is 1 minus cosine squared y. When I take the square root of both sides, I need to remember that the square root of sine squared y is the absolute value of y. And to deal with that absolute value, that means sine y will be either plus or minus the square root of 1 minus cosine squared y. And it's not that both of them work, or I just get to pick one at random. That's going to be determined by whether y is an angle whose sine is positive or negative, and that's determined by what quadrant it's in. So that's where I need to use this information. Y is between 0 and pi. That corresponds to quadrants 1 and 2, and those are the quadrants where sine is positive. So I know that sine of y is bigger than or equal to 0, so I can say it's the positive square root. So then I can come back to this part of the board, and I can replace sine y with 1 minus cosine squared y. And I just sort of emphasize that's cosine of y squared, and cosine of y is x. That's what arc cosine means. Okay, so we get negative 1 over root 1 minus x squared. Just one quick note. I said that you should simplify this so that you didn't have any trig or inverse trig. And if you followed these steps, you were never really tempted to have trig or inverse trig if you knew that you were trying to get rid of the y's. Another way that you could have gotten rid of the y's is you could have said this is negative 1 over root 1 minus cosine of y is arc cosine of x, and that quantity is squared. I don't want you to write it this way. Cosine of arc cosine of x is just x. That's definitely the simpler way of writing it. So rather than replacing y with arc cosine of x, replace cosine of y with x.